Hello everyone. Today we are going to be doing the lesson on 10.8, which is geometric probability. So you'll need these notes and you'll need the tip chart. We did all the circle vocabulary. Today we're going to do the geometric probability one. All right, so before we do geometric probability, let's talk probability in general. We'll go ahead and put this definition down. The definition of geometric probability is probability, of course. Probability that uses a geometric model. Geometric model. Okay. But before we do geometric probability, let's talk probability in general. So I was taught that geometric probability means that you just do part over whole. Like, for example, if I said, what's the probability, like, let's say Mr. Copeland's gonna walk into our classroom, what's the probability he's gonna choose a 9th grader to go help him stack chairs? Well, you would take the part of the class that's 9th graders, that number, and you would divide it by the whole number of students in the class, and you would either write it as a fraction or a decimal or a percent, and that's the probability that he would choose a 9th grader from our class. So that's like a general probability question. All right, so think back, let's just talk a little bit about probability. So think back to when you were probably in middle school, you did probability, maybe late elementary. Maybe you had a problem something like this. Now this is just to talk background about probability. You might have a problem that says that your room is dark and you have this drawer of socks, and in the morning you're just going to reach in and pull out a pair of socks from the drawer. And let's say you have 3 blue pairs of socks and you have 5 black pairs of socks and you have 2 white pairs of socks. What's the probability that if your room is dark and you reach in to grab a pair of socks, what's the probability you're going to pull out a blue pair of socks? So the way that works is the number of blue pairs, the part of the socks that are blue, there's 3 of them. Out of the whole number of socks, there are 10 total pairs. So you have a 3 in 10 chance of pulling out a blue pair of socks if you reach in there in the dark and pull out some socks. That's basic probability. Now, a good thing to know about probability answers is that probability answers will always be between the number 0 and the number 1. Probability will always be between 0 and 1. And the reason that's good to know is because that helps you check the reasonableness of your answers. Let me explain to you why it would have to be between 0 and 1. Suppose we have this same scenario and I ask you, what's the probability that you're going to reach into that drawer in the dark in your dark room and pull out a yellow pair of socks? Well, if you have 3 blue pairs and 5 black pairs and 2 white pairs, the probability you're going to pull out a yellow pair of socks is 0. That's not going to happen. If it's never going to happen, it's a probability of 0. Because it's 0 yellow pairs out of 10 total pairs. So that's a probability of 0. If it's never gonna happen, probability 0. Now, what if I ask you in this scenario, what's the probability that you're gonna reach in there and pull out either a blue pair, a black pair, or a white pair? Well, all of them are either blue or black or white. So every time you pull out a pair of socks, you're going to get either a blue pair, a black pair, or a white pair. So every single time, 10 out of 10 times, or 10 pairs out of 10 pairs, is going to be either blue, black, or white. So if it happens every time, that's a probability of 1. So if it never happens, that's a probability of 0. If it always happens, that's a probability of 1. So probabilities are always, always between 0 and 1. Now, sometimes they ask you to write probabilities as percents. So they might say, what's the percent of the time that you're going to pull out a blue pair of socks? Well, 3 out of 10 as a percent is 30%. And so, you know how I told you the answer is always between 0 and 1? Well, some might say, well, that's not between 0 and 1 because the answer is 30. But remember that percent means per 100. That's the root word of century. Century is 100 years. So I don't know if y'all knew this, but I'm sure you did. That percent means per 100. which means divide by 100. So 30% means 30 divided by 100, and that reduces to 3/10 or 0.3, which is a number between 0 and 1. So even if it's in percent form, that is a number between 0 and 1. Okay. If you look up, just one more quick thing about probability in general, if you look up the definition of probability in like a math textbook, it would say the number of favorable outcomes over the whole number of cases. Hold on just a second. I just got interrupted by my dog. Hold on. Hey, Kale. The puppy has a pencil. You think you can get it from her?
Well, not tonight, spaghetti.
All right, sorry about that interruption. Okay, let's talk geometric probability. All right, so there are two cases of geometric probability. And so one model would be like a segment model. Hey, Kale, can you do it kind of quietly? Because I'm...
I got it.
So A, B, C. All right, so they'll have questions something like this. They'll say a point is chosen at random. They'll usually name that point. So they might name it point S or point H or something like that. And they'll say a point is chosen at random from this segment. What's the probability that it's lying on one of the smaller segments? The question will look something like this. What's the probability that point S is on segment BC? So a point S, is chosen at random. What's the probability that it's going to be on this segment BC? So since probability means part over whole, the favorable outcome would be segment BC. Now remember, if there's no bar over it, it means length. So the length of segment BC over the whole segment AC. That means length of segment AC. So it's part over whole. That's how you would calculate that. And then the other type of model, so one model would be a number line. The other type of model would be from like a shaded region like this. And now you can see why they're putting this material, geometric probability, in the area chapter, because the question will look something like this. What's the probability that if you choose a point at random from this entire rectangle, what's the probability that it will lie in this shaded triangle, or shaded region, they might say. So they'll write the question like this. What's the probability that point S is shaded, or in the shaded region? This just means probability of this happening. Probability of this happening. Okay, so the way you would do this is why it's in this chapter. You would put the shaded part, which is an area problem. Area of the triangle. You would put it over the area of the entire rectangle. Area of the rectangle. So it would be the shaded area, the triangle, over the entire area, which includes the triangle. It would be this rectangle area. So again, it's part over whole, the shaded part over the whole part. Some questions like this one, see, sometimes the shaded area is kind of detached from the bigger area, but on a problem like this, you can divide it. You can draw something called an auxiliary line. Auxiliary line is just when you add a line to the picture to divide it up. You can see that the answer to this probability question now is 1/2, because this rectangle, half of it is shaded, and this rectangle, half of it is shaded. So of the whole rectangle, half of it is shaded. So this answer is 1/2. Some problems can be divided like that. A problem like this could not be done that way. You would have to actually calculate the area of the triangle and calculate the area of the rectangle. So that is what geometric probability is. Okay, now we're gonna do some examples. This box just says what I put on your tip chart. You can put the date on there and your name. So this would be part over whole. If probability that point S is on BC would be this length, that part, over the whole thing. In this case, the whole thing's AD. And then this one would be one of those area models where you would find the area of the shaded part and put it over the area of the whole rectangle. All right, let's do some problems. Question number 1 says, a point on segment AG, the whole segment, is chosen at random. They want us to find the probability that that point chosen at random is on segment BE. So segment BE is right there. That's the part. That would be the successful outcome, or the favorable outcome, I think is what they use. So this would be 3 spaces. See, I don't have any numbers on there, but since it's evenly divided, you can just count how many spaces are on segment BE. That's the part. And the whole thing would be 1, 2, 3, 4, 5, 6 spaces. So that is 1/2. If you choose points at random, half of the time they're going to be on segment BE. And before I calculated it, it would be written like this: BE over AG, like that. Okay, this doesn't seem like it, but it's a linear model like this. It's a line segment model. It says a bus stops every 15 minutes. If you arrive at a random time, find the probability that you're going to wait for 5 minutes or more. So here's a bus. And here's another bus. And that bus arrives every 15 minutes. Okay, so this bus just left. If you arrive right after that bus leaves, you're going to wait for 15 minutes. If you arrive here, you're going to wait for 14 minutes, and so on. So let me split this up into thirds like this, just so we can think about it. Now, you don't have to draw this. There are some of you who would answer this question without drawing this, but you guys know me by now. I draw just about everything. So anyway, these are just arrival times. So, or wait times. If you arrive here, you're waiting for 14 minutes. If you arrive here, you're waiting for 6 minutes. This is 0, that's when the bus arrives. Okay, so the question is, if you arrive at just a random time in this time interval, find the probability that you're going to wait for 5 minutes or more. So 5 minutes or more is going to be this amount of time right here. And since I divided it into thirds, just so we could think about the time a little easier, this is the part of the segment where you're waiting for 5 minutes or more. So 2 of the units are shaded out of 3 spaces, so 2/3. Or you might think that if you're waiting for 5 minutes or more, that's a 10-minute period of time. If the whole thing is 15 minutes, so 5 minutes or more would be 10 of those minutes out of 15, and that reduces to 2/3. All right, example number 3. It says, find the probability that a point chosen at random from the square is in the triangle. So since the triangle is joined to the square, this would be one of those problems that you could do like this. And so I'll show you this in a couple different ways, okay? So one way is to draw that auxiliary line, and then you can see that the triangle is half of the square, because when I look at this half, you can see that half of it is shaded, and when I look at this part, you can see that half of it is shaded. So half of the whole thing is shaded. So the answer to this question is 1/2. So that's one way to do it. You can do that so long as the shaded area isn't separated from the outer area like that. Okay, now what we learned is on the tip chart, what we said on the tip chart is the area of the triangle goes on the top, that's the shaded part, and the area of the square goes on the bottom, because it's shaded over whole. It's part over whole, shaded part over whole thing. Well, the area of a triangle is 1/2 base times height, and the square is base times height. You can kind of see from here that it's going to be 1/2 because the BH's cancel. But if we complete this formula, 1/2 times 12 times 12, because the base of the triangle is 12 and the height of the triangle is 12, it's the same as that. And base times height is base times height, 12 times 12. And you get 72 on the top, and you get 144 on the bottom. And if you reduce that, it reduces to 1/2. So even with the formula, that method works. It's area of the part over area of the whole. Okay, we have 2 more. This printed a little funky. That is supposed to be a circle. It looks a little bit ovular. It got a little squashy, but I tried. So it's supposed to be a circle. And if that distance right here is 10, and it's a circle, then so is that. So this is 10. It says find the this one you would not be able to use that method where you just draw auxiliary lines, because we've got these curvy places. You know, so if we draw an auxiliary line, you still can't tell what part is shaded because it's curvy. So we're gonna have to do that method of area of the circle. That's the shaded area. So remember, this top part is the shaded area over the area of the square. Okay, so we're going to be using area formulas. This is pi times radius squared. This is base times height. At any time when you're watching these lesson videos, you can pause and do the problem and then see if your answer matches mine. Remember, you're always welcome to do that because this is your own time, and however you learn best is what you should do. All right, if this whole thing is 10, then the radius is 5. So the diameter is 10, the radius is 5. Pi times 5 squared. And then the base times height, 10 times 10, you get 25 pi on the top, and you get 100 pi on the bottom. Just 100 on the bottom. And then that reduces, 25 over 100 reduces, this answer is pi over 4. So the probability of choosing a point at random and that point lying in that shaded part is pi over 4. Now, some people don't like that answer. I do. I think it's a fine answer. But remember, pi is about 3, so it's roughly 3/4. If you want to express it a different way, you can use your calculator, and pi divided by 4 is 0.785. So you could say that it's a 0.785 probability, or it's a 78.5% probability. So you could express it like that, which I like, or you can put 0.785, or you can put 78.5%. So all those are ways to express that answer, and that answer is reasonable, right? Because most of the square is colored, like 78.5% of it. So, so that answer is reasonable, and this probability is between 0 and 1, so that's just more confirmation that we're doing things right. Okay, example 5. This one is a hard one, y'all. So if you want to pause it and try it and then see how you do, that would be a good idea. But if you want to just watch, I'll show you. It says, find the probability that a point chosen at random from the regular polygon. So they're choosing a point at random from this regular hexagon. They want to know the probability that it's in the shaded area, these little tiny shaded corners. Now, before you even start, that's going to be a pretty low probability because the shaded area is tiny. So just keep that in mind when you check the reasonableness of your answer. All right, so you do shaded part, which I can't really call it a shape because what are those little shaded corners? So I'm just going to put shaded part over the whole hexagon. Whole hexagon. So that's what I'm actually doing. I'm doing the shaded area over the whole hexagon. So let's work on this shaded area. To find these little corners, you take the entire area of the whole hexagon And then you just subtract out the circle. And that'll leave you with these little corners. So we're gonna do hexagon minus circle to get those little shaded corners. So I'm gonna put shaded. Is the hexagon minus the circle. Okay, let's do hexagon. Hexagon, the formula is 1/2 perimeter times apothem. Again, you could pause this and try that part if you want to. Perimeter. This side is 5.8. There are 6 of them. So that number right there is 5.8 times 6. 5.8 times 6. So 5.8 times 6, 34.8. 34.8. Now the apothem. See how they gave us this 10 over here?